so we are moving now to the following paper, and so it will be presented by Han-Min Park, who is from, are you still with the Seoul National University? Yes, so Han-Min received a BSc degree in electrical engineering from Seoul National University, a career in 2007, and MSc degree in electrical engineering computer science from the same university in 2009, and he is currently pursuing PhD degree in electrical engineering computer science, and his research interests include NoC design, GPU programming, many core cache architecture design, and low power processing. So, Amen. Very much.
Thank you. Good afternoon. My name is Han-Min Park from Seoul National University, and my supervisor is Professor Choi, also from Seoul National University. Today I'd like to present you our work for NoCArc 2012, which is position-based weighted round-robin arbitration for equality of service in many core network on chips. So we basically deal with the equality of service in the network on chip, especially the network is saturated by a specific traffic pattern, which is the hotspot traffic. We tweak the arbitration mechanism, exploiting the deterministic properties of the network on chip, for example, topologies or the routing algorithm, so that to develop a much simpler way to achieve the equality of service compared to the previous work. So I'd like to start my presentation with a brief description of a hotspot traffic pattern. The hotspot traffic is a traffic pattern in which some or all nodes in the network continuously send packets to a common destination node. And this slide here shows some properties of the hotspot traffic. I want to note that the XY routing algorithm is used not only in this slide, but also through all the slides of my presentation, because our idea depends on the deterministic property of the XY routing algorithm. So if you take a look at this left-hand side figure here, let's assume that some shared data or global shared blocks are stored in the top right corner of the network. And every other nodes are accessing those data by sending request packets, like as shown in by the arrows in here. Oh, by the way, the corners are common places for memory blocks, as in some of the state-of-the-art many core architectures, such as single chip cloud from Intel or the Tile 64 from Tyler Corporation. So the selection of the memory block to be located on the corner is not completely arbitrary. And so if because this node here is the only node that is processing all the request nodes from other nodes, we can easily guess that hotspot traffic makes the network saturated really fast, which is also shown in this graph on the right-hand side here. Here we plot the average packet latency versus the offered traffic. The offered traffic here means how fast each requesting nodes are generating packets per cycle to the common destination node. So if you take a look at here, the hotspot traffic makes the average packet latency grows really fast compared to other traffic patterns such as uniform random, bit complement, bit reverse, etc., etc. So there can be a research topic that tries to slow down the saturation speed of the hotspot traffic, which was as the one presented in DEC 2012, Design Automation Conference this year. But our interests don't lie there. What we focused was what happens after the network is saturated. So after the network is saturated, the fairness of the distribution of the service, in this case, the accepted throughput degrades or hurts very much. The figure on the right here shows that clearly. The common destination node here is 7.7 here, and the offered traffic is 1.0, meaning every node is generating one flip per cycle. The accepted throughput is measured by checking all the nodes that are received by the common destination node and asking where they come from. So basically, the accepted throughput of a specific node means how many of its requesting packets are received or processed by the common destination node here. So if you plot the minimum, maximum, and average value of accepted throughput as we gradually increase the offered traffic, we get the curve like this. Before the network is saturated, all trees looks almost the same. While on the other hand, after the network is saturated, they diverge very much. The average value converges around 1/63 because the one common destination node processes one flip per cycle, while other 63 nodes are sending packets. And if you look at the maximum value of the accepted throughput, it continuously increases, while the minimum value of the accepted throughput converges to 0. If you look back to this figure again, we can find out two patterns of the distribution of the accepted throughput. One is that the closer the nodes are to the destination node, the more throughput it gets. And the second pattern is that while the first pattern of the closer node getting the more throughput is true, it is not symmetric across this diagonal of the network. As you can see here, nodes along the x direction gets more throughput than the nodes along the y direction, even if they are at the same distance from the common destination node. This is because XY routing is being used, and the ordinary round-robin arbitration is being used. In the XY routing algorithm, the packets flows through the X direction first, and then goes through the Y direction. That means that these 7 nodes are serviced by the west input port of the destination node, while these 56 nodes are serviced by the south input port of the common destination node. So that if the common destination node gets one flip from the west input port and one flip from the south input port, and so on, then obviously the nodes here gets more throughput than the others because they are competing with fewer competitors. So this is one of our motivation for the work. Thinking if we weight the round-robin arbitration here, we might get the equality of service with low cost. So to show the results first, after some tries and errors, we get this. You can see that the distribution of the accepted throughput is perfect here. And one thing to note here is that the average value of the accepted throughput does not change because it reflects the overall throughput, accepted throughput of the network. But in this case, you can see that minimum and maximum throughput, accepted throughput also converges around 1/63, meaning perfect distribution is achieved. And here, the accepted throughput of the common destination node is 0 because it does not send any package to itself. So, I'd like to elaborate the idea later on. And before explaining the main idea of our work, I'd like to present you some previous works. The first one is large-scale computer networks, such as Internet, and it uses techniques like generalized processor sharing and fair queuing, etc., to achieve the equality of service. And the second one is age-based packet arbitration, where the older packets gets higher prestances than the younger packets. And it is presented in Supercomputing 2007, And the last one is probabilistic distance-based arbitration, where the packets that have traveled farther gets higher precedences. Why probabilistic? Well, in case of age-based packet arbitration, if one packet remained waiting to be granted in the input queue or queue, as time goes on, it gets age. It gets older, right? But in case of distance-based arbitration, if the packet remains in the queue, then they don't get more distance when they are waiting for their grant. So it should be probabilistic. So that means that the packets waiting in the queue might be starved. So the arbitration should be probabilistic. And yeah, it is presented in Micro here in Micro 2 years ago. The common weaknesses of these three approaches is that they are very much general, meaning that they don't assume any kind of network properties, such as topology or routing algorithm being used. The first one, internet, well, it expands arbitrarily, so it is impossible to assume such kind of network properties. In the second case and third case, even if their topology and routing algorithms are fixed after the network is formed, they just don't use the deterministic property of the network characteristics, and incurring some overheads. In case of the age-based packet arbitration, it must maintain the global age information somehow, or its estimation at least. And the overhead of maintaining the global age is also mentioned in here, which will be our main competitor, and I will explain this arbitration method as well as our idea throughout the slides, my presentation. So now I'd like to move on to the main section of my presentation, which is the elaboration of our main idea, position-based weighted round-robin arbitration. And the first topic is the motivation, and the motivation starts with the probabilistic distance-based arbitration. If we take a look at this 831 mesh network, and let's assume that the hotspot traffic, whose common destination node is 7, is flowing through it. So if the ordinary round-robin arbitration is used, because if you look at the router here, it gets packets from local input port here once, and then west input port here. So that each processor's being granted decreases geometrically, not linearly, as shown in this figure. The first one gets 1/2, probability of 1/2. The second one is 1/2 of 1/2 is 1/4. 1/2 of 1/4 is 1/8, something like that, and so on and so on. So in distance-based arbitration, so not linear weight, but geometrical weights are used, and this equation shows that clearly. Here the Cx and Cy are the contention degree, which are 2 here, right? 2 input ports are competing for the service from the output ports. And Hx and Hy are hop counts, which indicates that each packet, how far each packet has traveled up until now. Okay, this is fairly reasonable, but as I read the paper, I found out that they performed the experiments using XY routing algorithm, which is fairly deterministic. And I thought that if they are going to use XY routing algorithm, then why not use the deterministic property of the routing algorithm so that to achieve much simpler way to achieve the quality of service. So what we thought was this. If you look at the router 1 here, west input port and local input ports are competing the service through the east output port here. And the number of processors that is served by the west input port is 1, and number of processors that is served by local input port is also 1. So in case of router 1, we can use an ordinary ordinary round-robin arbitration. But in case of router 2 here, while it's the same that West input ports and local input ports are competing service through the East output ports, the number of processors that each input port should service differs. In case of West, it serves 2 processors. In case of local input port, it serves one processor. So we thought that if we weight the round-robin arbitration like this, we might get the equality of service throughout the entire network. So we established the design procedure for our arbitration algorithm, which goes like this, which is called position-based weighted round-robin arbitration. And it is a weighted round-robin arbitration whose weight varies according to the node's position in the network. So the design procedure goes like this. We first count the number of nodes to be served by each input port, as I explained before. And then the output port arbitration, meaning determine which input port should be serviced by each output port. This step is required because not all input ports are serviced by the output port. I think this listing of design procedure is not clear, so I prepared an example of 8x8 mesh network, and I want to present you how we can apply the design procedure to achieve the equality of service. So in this 8x8 network, the first step, counting the number of nodes to be served by each input port, goes like this. In case of XY routing algorithm, it looks like this, and in case of YX routing algorithm, it looks like this. If you take a look at this white node here, the input weights are 32, 5, 1, 2, and 24. These are just countings of the nodes that should be served by each input port. In case of YX algorithm, they are 4, 41, 16, and 3. These differences can be explained by using term models here. In XY routing algorithm, if packets start to travel in vertical direction, then they cannot turn to the horizontal directions to prevent the deadlock on the routing algorithm. And in case of YX routing algorithm, they are just opposite. If packets start to travel in the horizontal direction, then they cannot turn to the vertical directions. So this fact is reflected by the fact that the nodes on the 4 corners of the networks are dealt with differently in these 2 routing algorithms. In case of XY routing algorithm, for example, the top left corner nodes here are served by the north input ports because package flows like this. And in case of YX routing algorithm, the same nodes are processed by west input port because the package flows like this. Okay. Let's move on to the second step. The second step of determining which input port should be serviced by each output port goes like this. And if you take a look at the east output port of the white node here, the north input port, east input port, and south input ports are not serviced by the east output port, and that can be also explained by the term model. If the packets are from vertical directions, it cannot turn to the horizontal directions, so that the north input port and south input ports are not serviced by the east output port. And because XY routing is being used, the U-turn routing or the 180-degree routing is not allowed, so that the east input port is not serviced by the east output port. The blue box here shows which input port should be serviced by each output port. The solid lines are indicates the allowed input ports, while the dotted line here indicates the prohibited input ports. So this completes the design procedure, which is very simple. We just apply the weighted round-robin arbitration with weights determined by the design procedure I just have explained. And we sum up the input weights to get the refresh cycle of the weighted round robin arbitration. And if one input port gets granted, its input port weights decremented by one by one. And then if the input weights of one particular input port reaches 0, then it is not the corresponding input port is not granted until the next refresh cycle comes. The hardware implementation is not novel. It's from Professor Dali's book, Principles and Practices on the International Networks. It shows an arbiter for a single output port which serves 2 input ports. And each input port has its weights and its counters, and which are refreshed with the value of input port weights and decremented one by one when the corresponding input gets granted. And if the counter reaches 0, then corresponding request is masked. And finally, we have an ordinary round-robin arbiter here, as a who implements the weighted round-robin arbiter. And we added some simplification here. One issue in implementing weighted round-robin arbiter is what happens when not all input ports are requesting for the service through the one output port. As an example, let's assume that blue nodes here and orange node here are requesting, continuously sending packets to router 2.0, while red nodes here and white node here does not send any packets to router 2.0. Then if you look at the input port weights of this white node, those of active input ports will be decremented, while those of inactive input ports are not decremented. That means that there is the term that the input weights of the active input ports reaches 0, while those of inactive input ports remain. What should we do? So ideally, the sum of the inactive input port weights should be redistributed to the active input ports according to their input port weight ratio. That means in this case, the active input ports weight ratio is 1 to 2, and the remaining input weights are 1 and 4, which sum up to 5. So 5 should be redistributed to active input ports according to the ratio of 1 to 2. Well, actually, you cannot do that in integral values. So basically, we cannot follow the ideal method. If you look back to the Professor Dali's book again, he proposes 2 approaches for this. One is just wait until next refresh cycle comes, doing nothing. And the second one is to add one or more arbiter to redistribute the inactive input port weights to the active input ports. The first one of doing nothing is too wasteful in terms of the performance, and the second approach is too expensive in terms of complexity. So what we do is just ignore the active input ports weights and just use ordinary round robin arbitration. If you do so, we don't need any kind of additional arbiters, because if you want to do the ordinary round robin arbitration, we just ignore this part and use the existing round robin arbiter. So this table summarizes that if there is some request whose input port weight is not 0, then ordinary requests from input ports whose counter is 0 are masked, and weighted round robin arbitration is applied. And in case all the requests are from input ports whose weight is 0, then the requests from input ports whose weight value is not 0 are masked, and ordinary round robin arbitration is used. So basically, this is an estimation of the ideal approach. But if you remember the previous slide, even if we use this kind of estimation, we could get the perfect distribution of the accepted throughput. So estimation is useful. And one more thing to add about the hardware implementation is the comparison with the probabilistic distance-based arbitration. As I mentioned, it uses geometrical weight like this, which incurs exponentiation operations like this. Note that the basis of the exponentiation operations, which are contention degrees, is not power of 2, but general numbers. So the exponentiation cannot be reduced to simple shifters. And the hardware implementation, they first calculate the weights of the input ports, and they sum them and generate random number because it's probabilistic, whose maximum value is the sum of the weights. And finally compare weights with the random number generated to decide which input port gets granted. If you look at here, that you can see that all of these circuits are serially connected. And considering the fact that arbitration is usually on the critical path of the router, it can degrade the performance of the router itself. And besides this hardware overheads, to implement the probabilistic distance-based arbitration, each package should carry hop count information in their headers, which is not required by the routing algorithm, XY routing algorithm, but only required by the fair arbitration mechanism they propose. So that makes that might make packets longer, and that can be considered as an overhead. Okay, now the experimental results. I'd like to show you the throughput distribution when number of hotspots are varies, and the effects on other traffic patterns, because we only considered hotspot traffic, but how much effect it has on the other traffic patterns. So as I showed you, for one hotspot case, the perfect distribution is achieved, and in case of two hotspots, also almost perfect distribution is achieved. In case of 4 hotspots, even though we have some operations here, if we compare the results to the ordinary round-robin arbitration, there's still better results can be achieved. And finally, we've got latency throughput curves for various synthetic traffic patterns to see how much effect it has to set the input port weights, only considering the hotspot traffic. So in cases of uniform random, bit complement, tornado, and neighbor traffic pattern, the performances are almost the same. But in cases of bit reverse and bit rotate, well, position-based weighted round-robin arbitration degrades the performance of routers in terms of saturation throughput about 19%. One thing I want to note here is that it is not a hard task to change the input port weights in runtime, because it's just adjusting the value of input weights registers. So if the programmer knows that the behavior of the application can harm the performance of the network on chip, and he or she also knows the statistical pattern of the application's behavior, then prior to the actual execution of the application, the programmer can program the network so that the network on chip can operate as the programmer wants. So here comes 2 future works for this topic. One is how to determine the input port weights when traffic patterns other than hotspot traffic is considered. And the second thing is that instead of programming the input weights manually, we can make arbiters adaptive, meaning it dynamically changes its input port weights according to the traffic pattern that flows through it. So finally, my conclusion. Well, we proposed position-based weighted round-robin arbitration for quality of service in many core analysis, and it is shown that the deterministic characteristics of network on chips can be exploited to provide equality of service with simple weighted round-robin method. And although optimized to the hotspot traffic pattern, the proposed arbitration scheme does not degrade much against other traffic patterns. And this concludes my talk. And if you have questions, please feel free to ask me.
Very nice. I think any questions, please? Do you think that, well, basically, when you talked about multiple hotspots here, or maybe things that are becoming more complex, do you compute the weights essentially with respect to each hotspot, and then you do some kind of superposition of these, or how do you decide for the multiple hotspots on the weights of arbiters?
Actually, there is no difference between the design methodology does not depend on the number of hotspots.
So it doesn't depend because each point is independent of the hotspots, but it's just purely geometric based on the coordinates of the point. So if you have multiple hotspots, so this calculation is independent where the hotspots are. Yes.
Yeah.
So it's for each point you compute. Yes. Okay. So, but if you know something about where the traffic is going, can it help or not?
Yeah, it can. I think it can help. One important thing is that application's behavior should be statistically defined. So if the application's traffic pattern is statistically defined, then I think, well, that was one of our future works, but according to that statistical results, we can calculate a kind of optimal input port weights for every node's internet.
So, suppose that you've got multiple possibilities for having some kind of attractors here in the network. Do you see how these can be computed in a relatively simple way, so that you don't have to run multiple waves of communication of the information about the attractors?
Oh, simpler way. I think we should consider that from now on, but we haven't think about more simpler way than this.
Because I was thinking about some kind of maybe superposing here geographical information of each position and their relation to those points of interest, and then having maybe, I don't know, maybe it's a bit like that dynamic programming, so that you will propagate data, maybe having an additional fabric.
Yeah. So instead of calculating from the ground, we can just superpose some well-representative traffic or the patterns, so that simply we get the
I mean, definitely starting with hotspots, positioning of hotspots.
I think we can do that, or we should consider that.
Okay. Right.
Can you go back to the result, like 2, 3, 4 hotspots? Yes. My feeling that, I mean, when we increase the number of hotspots, maybe we'll go for 8. It's, I mean, the traffic, it's already distribute itself without need be position based, right?
Oh yes.
I mean, when it's 1, it was really extreme, so your method worked really well. With 2, the same, but if you go for the 4, there seems not bad, not much difference.
Yes, that's right.
They're getting
so if we impose another maybe 2 hotspots in the middle, it will be equally well. Why we are doing all this extra hardware to design this weighted round robin? Because it sounds normal. I mean, we will have 4 memory out of 64 or 8. It's logical, not.
But let's say you are an application programmer, and you can intentionally place the hotspot considering the architecture of the network, or you can just regard the networking chip as a black box and application programmer just programs it. Then those kind of general situations, the hotspots can be not evenly distributed. In such cases, if you use round robin arbitration, then the distribution of the service might be unfair. So yeah, that can be the reason.
Okay. So any more questions? If there are no more questions, Hanmin, thank you very much.